So hello friends, it's Relativistic here, and today we are going to discuss about relativistic Doppler's effect from four vectors perspective. So before we start, you must know two things. One is matrix form of Lorentz transformation, and you must have the clear concept about four vectors. Okay, so I hope you know these things. If you don't know, then first study those two topics, then come to this video. Okay, so before we start, please subscribe the channel, okay, and share with your friends, inspire me to create new content for you, and hit the thumbs up button as well, and also hit the bell icon so that you get notified when new video will be uploaded, right? So now let's start. So relativistic Doppler's effect from four vectors perspective. So first let us consider two inertial frames. Suppose one is S. This inertial frame is S and its origin is O. So this is your x-axis, this is y-axis, right? Now let us consider another system of coordinates or inertial frame, that is suppose S dash. Here this is x dash, this is y dash, right? Now you see, it is not necessary that these two frames are in the same plane. Okay, they may be in this way, like this also. Okay, or they may be parallel also, like this. Okay, one is this, another is this. May not be in the same plane, like this. Okay, so these two may be on the same plane, or maybe in two different parallel planes as well. Okay, and they may be at the same level or at different levels as well. Okay, so hope you have understood. So let me draw this way. Just wait, let me draw this way. One frame is this is the frame S. Okay, this is the frame S, this is the frame S dash, and this is origin O. Here is the origin O dash, right? Suppose we have a source of light here. Here we have a source of light, and here at O dash we have an observer. Here we have observer, or you can say it is not necessary there will be a human being, or there may be an instrument detecting light or any other signals, okay, that will be emitted sent from this point. Okay, so if I consider here a source of light that emits light, suppose this emits light, and here we have an observer, okay, at O dash, and this angle is suppose phi. Let me take this angle is phi, right? So now you see, frequency of this light wave is suppose with respect to this frame is suppose nu, and with respect to this frame is suppose nu dash. Okay, now let me clear one more thing. Okay, if I write this will represent gamma. If I write this represents nu. Nu means here frequency, and gamma is nothing but you know, in relativity you have got 1 by root over 1 minus b square by c square. Okay, so don't be confused. Okay, if I write like this represents gamma, and this is nu, which represents frequency. Okay, now let me clean it. Okay, now first you have to write, let us consider two inertial frames. Let us consider two inertial frames S and S dash. Okay, S and S dash, and let us consider that S dash is moving with velocity with velocity v I cap. V I cap means, that means this is moving along x-axis. Okay, so instead of writing this is moving with velocity v along x-axis, to make it shorter I have given here I cap, so that you can understand that it is moving along x-axis, right? Moving along x-axis, positive x-axis, that's why here it is I cap. Okay, this is I cap, v I cap. Okay, relative to s, relative to s, right? So now an observer at Odes, the observer at the origin Odes, so just wait, let me write here, at the origin Odes of the frame S dash receives light signal from the source at O of frame S. Okay, right? And I hope you know the Doppler effect, that you have, I think you have already studied about Doppler effect in senior secondary level in chapter sound. Okay, so hope you have that idea. So here you see, let me mention one more thing. Signal from this signal receives light signal, okay, and of frequency nu, suppose. Okay, now you see that in this case what we can do. So now we are going to write the momentum, 4 vector momentum. Okay, momentum 4 vector. Let me write that here. You see, in S frame, momentum 4 vector, momentum 4 vector that is p mu. We used to write p mu. Okay, momentum 4 vector p mu, which can be represented by p and I e by c. So we know in space we used to consider 4-dimensional space. Okay, so this p has 3 components. It has 3 components along x. One is x component p1, and one is y component, and another is z component, x, y, z components, and another x, y, z, and there is another axis which is time axis, and this is the components of the 4 vector momentum 4 vector along the time axis, right? So hope you have understood this, right? So now here you see, so if this is the frequency of light, then energy emitted from this source in the form of light is given by h nu, where h is Planck's constant, right? And nu is the frequency of light. Okay, nu is the frequency of light. Now here you see this p mu vector. Here we're going to have three components of this, that is h nu by c cos phi, right? Cos phi. Another is h nu by c sin phi. Okay, then here you see we are considering only two axes for simplicity. So here its motion is that means on xy plane, not along z axis. That's why z component will be 0. Momentum of the z component will be component of the z component of the momentum will be 0, and that of time time component is I. Here instead of e we can write h nu by c, right? Hope you have understood this, right? So momentum is given by h nu by c, right? H nu by c. Here one more thing. So h nu by c, one is cos as a cos component, another is sin component. Here it must have two components, one is x component, another is y component. Hope you have proper idea of vectors. So if this angle is phi, then you should get one is this is your x component, sorry, this is your y component, this is your x component. This phi is made along with the x-axis. That's why this should be cos phi, right? This should be cos phi and this should be sin phi, right? And here you see we are not considering the z-axis here. That's why z component is 0. That means these are the two frames. This is the observer. Okay, this is moving in the xy plane or plane parallel to xy plane. This is not moving in such a way. That means it is not moving along in 3D. It is moving in 2D. Okay, that means in a plane, it is moving in a plane. Okay, we can consider that way. So that's why z component is 0, right? So now here remember one more thing, that this I is not the unit vector of x component. This is not the I cap. Okay, this is the imaginary I. Okay, this is the imaginary number I, right? Because in 4 vector you have got, suppose this is the position vector, then with x mu it can be represented x, or it was represented by r comma I c t. This way, this is the time component, right? In space 4 vectors, right? We used to represent like that. I is the imaginary here, I is imaginary here. So okay, now what we can do, we can take this part common. We can take this h nu by c common. Let us take this common. H nu by c is taken common. Then what we gonna have? Then we can have h nu by c, and within bracket here we're gonna have cos phi comma sin phi comma 0 comma and I. That's what we're gonna have, right? Just pause the video and note these things. Okay, so because I'm gonna clean this part, because there is not enough space in this board, so let me clean it. So here you see, pause the video, just let me clean this first. So hope you have noted this. Okay, Stupid. Now you see, so all these things I have written with respect to disk frame as. Now let me write these things with respect to the observer. Okay, that means in S disk frame. Okay. From this, if you have written this, then just write first. Let me write here. In S dash frame, in S dash frame, momentum 4 vector momentum 4 vector. So that's gonna be that. Let me represent it by p nu dash. That's gonna be, you know, p dash comma, and the time component is I is nu dash by c. Here let me write nu dash by c. This is the frequency of light which changed due to the motion of relative motion of the frame. Okay, relative motion of this frame. So there will be a change in frequency. Okay, and the new frequency of the light for the observer. Okay, this is the frequency of the light for the observer due to Doppler effect, right? The frequency of light for the observer, right? Now you see again this one also, this p dash also have three components, p1 dash, p2 dash, p3 dash, right? So here you see this is this is nothing but p1. You can take it as a p1, and this is nothing but p2, right? And this one, this 0 is p3, and this is taken as p4, right? And similarly here this will have p1 dash, p2 dash, p3 dash, and this one is p4 dash. Okay, so and then what we can write here, we can write this way. This is nothing but is nu dash. Again we can let me write this system directly. Okay, what if you take the h nu dash by c common, then what you're gonna have within bracket, you're gonna have cos phi dash comma sin phi dash comma 0 comma I. That's what you're gonna have, right? So this one into cos phi dash is here p1 dash, and this part into cos sin phi dash, that is p2 dash, and this one into 0, that's going to be p3 dash, and this one into I, that's going to be your p4 dash, right? So hope you have understood this, right? So let me consider. Okay, yeah, let me clean this first. Okay, just give me a second. Is nu by c cos phi, right? Okay, now we're going to use the Lorentz transformation. Okay, we're going to use the Lorentz transformation. Right. So here you see according to Lorentz transformation, just wait, what let me write a matrix form of Lorentz transformation of this momentum. So here, so let me use another marker here. Okay, so what we can write here: P1 dash, P2 dash, P3 dash, and P4 dash. You see, these are the four components of P mu dash, okay, which is equal to, that's gonna be your, here we're gonna have gamma, this is gamma, okay, this is not mu, this is gamma, and I have already told you what is gamma. Gamma is equal to 1 by root over 1 minus v square by c square. This is what gamma, okay. Then 0 0 I and h nu by c, gamma 0 0, then I v into gamma divided by c. Then again here 0 1, then 0, right, 0. Next should be 0 0, your then here 1, this diagonals here again you're gonna have gamma, okay, just this is 0. Then this same thing comes here but in opposite in sign. Here the gamma, that should be gamma, okay, this is v, this is gamma divided by c, then these two are 0 and 0. And here we're gonna have the components of P mu, those are P1, P2, P3, P4, right, P4, right. Now you see here, in short, these things are represented this way, can be represented this way according to Lorentz transformation. P mu dash is equal to summation, here we have 4 and here we have mu, then a mu nu, then we have p dash here, right, and this is nothing but this matrix, right. Hope you have understood this. Now we are going to find the relation between this frequency that observed by this observer and this original frequency of this light in this frame, right. So hope you have written all these things. Now let me clean this part, okay. So now we're gonna deal with this matrix only, right. Okay, now you see this column matrix represent the components of this P mu dash, and this column matrix represent the components of P dash, right. Sorry, not P dash, this is supposed to be P mu, not P dash, this is supposed to be P mu, okay, sorry for the mistake. Okay, now you see what is the time component. This is the time component here. If we take the time component, okay, so let me find the relation of this time component. Now with this time component, okay, let's take this two. Now you see here this P4 dash, that's going to be equal to its corresponding row into this column then what you're gonna have, minus I v, sorry, this should be gamma, not nu, gamma by c into p1, then plus 0 into 0, 0 into p2, plus 0 into p3, then plus here we're going to have gamma into p4. That's what we have got. So if you check your notes, if you have noted, check the notes, that p1 is nothing but here you see we already have got that p mu is equal to h nu by c cos phi, right, and h nu by c sin phi. Then next component was 0, then I h nu by c. That's what we have got. We have already written that. So this is nothing but p1, this is p2, and this is p3, and this is p4, right, p4. Now let us replace these values by those. Okay, so then what we're gonna have here, and we know p4 dash, this p4 dash. So we also got that p mu dash is equal to that h nu dash by cos phi dash, and similarly h nu dash by this should be nu, okay, h nu dash by c sin phi dash, right. This is p1 dash, this is p2 dash, and p3 dash is 0 again here. Then p4 dash, this is p3 dash, and p4 dash is nothing but I h nu dash by c. That's what we have got. So here we can write I h nu dash by c. That's what we can write. Okay, then let me clean these things. So if you have not understood, let me tell you again that we had written that p mu dash is equal to h nu dash by c cos phi dash, comma sin phi dash, comma 0, comma I, right. If you multiply with this one, that gives p1 dash, right. This one into this one, it gives p2 dash, and this one into 0, that gives p3 dash, and this one into I, which is nothing but this one, which is p4 dash, right. Hope this thing is clear to you, right. So let me clean it. Okay, then here you see these two components become 0, right. 0 into anything is 0. That's it. Now you see here we have minus I v into gamma by c, and pi1 is nothing but h nu by c cos phi, right, and plus gamma p4 is nothing but, what was p4, this is the p4 I h nu by c. That's what we have got. Okay, now you see let me clean this part. Okay, so hope you have noted all these things. Just let me clean it. Let me keep the last step only. Okay, now you see what we're gonna have here, what we can take common here. Let me find a common part, just wait. So here you see we have common this h nu by c Just do one thing. Let me keep this part. Okay, so let me keep this part. Let me take gamma common, h nu by c, gamma h nu by c. Let us take this part common. Okay, then what we're gonna get, if we take gamma h nu, this is nu and this is gamma by c, then within bracket we're gonna have minus I v, sorry, let me take I also common, then within bracket we're gonna have v by c, one c is taken common, cos phi plus gamma is taken common, h nu by c is also taken common, so here we're gonna have I is also taken common, so we're gonna have 1 here, right? So that's why for the terms gonna be cancelled here. So here we have sorry, let me write here is, so here you see I is nu dash by c, that c cancel, h also cancel, I also cancel, right? Then we end up getting nu dash is equal to nu, this can be written this way, positive can be let me write the positive one first, then the negative term, so that means 1 minus v by c cos phi, let me write that way, and there should be a gamma, okay, into gamma, okay, I forgot to put the gamma here, this nu and this is gamma, okay, don't be confused, this is gamma, this is nu, and nu dash and this is nu. I have already told you that gamma is equal to this, where c is the velocity of light, right? So 1 minus v by c cos phi by root over 1 minus v square by c square. Okay, so this is the relativistic Doppler effect. Okay, right? Now let me explain two special cases here. If the two sources are at the same level, this two, like this, right, on the same plane, and these are this source of light and the observer both are in the same line, on the same line, and in that case this angle phi gonna be equal to 0. Let me write case 1 here, this phi angle is equal to 0. Okay, if phi is equal to 0, then what we're gonna have, then nu dash, that's gonna be equal to nu 1 minus cos 0 is 1, so v by 1 minus v by c, and here 1 minus v square by c square. Now you see this 1 minus v square by c square, 1 minus v square by c square can be considered as 1 square minus v square by c square, and so applying a square minus b square formula, a square minus b square is equal to a plus b into a minus b, then you can write 1 plus v by c into 1 minus v by c, right? And you see, and if you write this whole thing under root, then you can write this way. If you give a square here, then you can write under root here, right? So now this root is not only on the denominator, so here both the denominator and numerator are now under root. Both the numerator and denominator are under root. So here, and if you apply the a square minus b square formula, then it can be this. It can be written this way, right? Now you see, you can cancel this one, right? So that's why you're gonna have, so we end up getting nu dash is equal to nu root over 1 minus v by c divided by 1 plus v by c. 1 minus v by c by 1 plus v by c, and this is called longitudinal, this is called longitudinal Doppler effect. This is called Doppler's effect. Okay, so hope these things are clear to you. Now what if these two sources are in parallel plane? Suppose let me take this way, they are in parallel planes. Here in this frame we have the observer, and here we have the source. They're at the same level, and this is moving in this way, right? For this observer, which is looking at this frame, for him, here you see, now this angle will be 90 degree, right? So that, let me consider that way. This is the frame now, this is the frame, and here is the source, and here is the observer. Okay, so this is the light. Okay, now this light is suppose, now this angle is suppose now 90 degree. Okay, right? That means these are the two frames now. Hope you can get it what I am saying. So in that case, so let me okay, let me clean these things. Let me clean the diagram as well. Now you see, case 2, if phi is equal to 90 degree, okay, if phi is equal to 90 degree, then what we will have, this nu dash is equal to nu into cos phi is equal to cos 90 is 0, that's why here we will have 1 by root over 1 minus v square by c square. That's what we're gonna have, right? Okay, so hope you have understood this. Now you see what we can do here. Nu dash, this is simply, you can write, nu by root over 1 minus v square by c square. So this is nothing but your transverse Doppler effect. Transverse Doppler's effect. So hope these things are clear to you, right? So enough for today. So that's all. Thank thank you for watching. See you in the next video. Okay, bye bye.